Alpha. It is symbol for large signal CB current gain. It is actually the ratio of collector current change from cutoff to emitter current change from cutoff. Its value is always less than 1. For a good transistor, it is very much near to 1. Roughly it is 0.99. Beta is symbol for large signal CE current gain. By definition, it is the ratio of change in collector current from cutoff to change in base current from cutoff. Usually its value is large. Typical values are 75, 100, and alpha and beta. These are related. Alpha has certain significance as it is used in describing transistors' internal currents. Beta's significance is that it is widely used in the design of transistor biasing circuits. In locating the operating point appropriately, it is highly useful. Apart from alpha and beta, we also come across emitter injection efficiency, which is the ratio of current injected into base to total emitter terminal current. Base transport factor is another parameter which gives some indication regarding what to do to have better performance from a transistor. Alpha, beta, gamma, B, these are all interrelated parameters pertaining to BJTs. Electronic devices, BJTs, BJT problems, series on semiconductor devices and circuits, lecture number 3.12. Bipolar junction transistors or BJTs in short are three-terminal semiconductor devices. These are active devices. These are widely used in the design of analog amplifiers, in the design of oscillators, in the design of feedback amplifiers, tuned amplifiers, and they find several such applications. In the present session, we focus on problems set around the currents, terminal currents and internal currents, and their interrelation. In the problems, we can also find the interconnection between large signal current gains, internal currents, and external currents too. Now, let us move further. We begin the session with problem example 1. Find the base current and CB-DC current gain alpha in an amplifier circuit in which emitter and collector currents are 10 milliamperes and 9.8 milliamperes. Also find the part of emitter current that reaches the collector terminal when IE, that is emitter current, is 12 milliamperes. Problem is quite simple. Solution: base current is emitter current minus collector current. Emitter and collector currents are given as 10 milliamperes and 9 milliamperes. Substituting, we get base current as 0.2 milliamperes. Alpha, which is a CB-DC current gain, it is approximately minus IC by IE. Collector current is given, emitter current is also given. The ratio can be determined without much difficulty. It turns out to be 0.98. So base current, it was determined, alpha was also determined. Now another part is there in this problem. Find the part of emitter current that reaches the collector terminal when IE is 12 milliamps. The part of emitter current that reaches collector terminal designated as IPC1 in case of PNP transistor, INC1 in case of NPN transistor. This part is equal to product of alpha and emitter current. Emitter current is available, alpha is available, hence their product 0.98 into 12. It can be determined. It turns out to be 11.76 milliampere. Hence, the complete solution to the problem is obtained. Another problem, example 2. Given that alpha is 0.95 and emitter current is 10 milliamperes, find collector and base currents. Also find gamma when B, base transport factor, is 0.8. Alpha is given, it is 0.95. Alpha is approximately minus IC by IE. So 0.95 is equal to IC by IE. IE is given as 10 milliamperes. So it gives IC as 9.5 milliamperes. IB is emitter current minus collector current. Emitter current is 10, collector current is 9.5. Therefore, base current turns out to be 0.5 milliamperes. We are asked to find out gamma. That part we tackle now. Assume a PNP transistor and the part of the emitter current that reaches the collector terminal is IPC1 is alpha into IE. Alpha is 0.95, IE is 10. Therefore, IPC1 becomes 9.5 milliampere. When B equal to 0.8, B means base transport factor. The whole current IPE is IPE in total emitter current. IE is IPC1 by B equal to 9.5 by 0.8 equal to 11.875. Now gamma can be evaluated as IPE by IE. Turns out to be 1.1875. Same result can be obtained when we consider an NPN transistor. Another problem, example 3. Find value of beta for a transistor with an alpha of 0.95. Also find the value of alpha when beta is 250. Solution. This problem is based on interconnection between alpha and betas. Beta is alpha by 1 minus alpha. Alpha is beta by 1 plus beta. When alpha is 0.95, substituting, beta can be determined as 19. When beta is 250, alpha can be found as 0.99. Another problem, example 4. Find the value of emitter current for a transistor with a beta 100 when A, the base current is 30 microamperes and B, the collector current is 10 milliampere. Solution process. We can consider collector current relation, a popular relation. IC equal to beta plus 1 ICO plus beta IB. ICO usually is very small and hence it can be neglected. When it is neglected, IC becomes equal to beta IB. Beta is available, IB is available. Therefore, IC can be determined with no difficulty. It turns out to be 3 milliamperes. Now, emitter current. Emitter current is base current plus collector current. Always using the available values of base current and collector current can be found as 3.030 milliamp. Now IB. IB is from this relation. IB is IC by beta. Beta is 100, IC is 10 milliamperes. We are dealing with part B. So IB is determined, it is 0.1 milliamperes. So IE is 0.1 plus 10. As already mentioned, emitter current is always base plus collector currents. In case 2, it turns out to be 10.10 milliamperes. Another problem, example 5. For a transistor with a beta of 150, find collector and base currents if the emitter current is 10 milliamperes. Beta is given. From beta one can find alpha. Solution process, alpha is beta by 1 plus beta. It turns out to be 0.99. Alpha is roughly, it is IC by IE when we neglect the negative sign. So IC is alpha IE. It turns out to be 9.9 milliamperes. IB is IE minus IC. IB is 10, emitter current minus collector current 9.9 milliamperes. It turns out to be 0.1 milliamperes. Another problem, example 6. Determine base and emitter currents in the transistor circuit when collector current is 60 milliamperes and beta is 150. Solution process. Collector current, output current, DC current, DC output of BJT. This is the relation IC equal to beta plus 1 ICO plus beta IB. Roughly it is IC equal to beta IB. From this, IB is IC by beta. IC is available, beta is available, IB can be determined. It turns out to be 0.4 milliamperes. IE is base current plus collector current. In the present case, it turns out to be 64 milliamperes. Notice, this is emitter current. This current travels through base layer to collector, and while traveling, partly it drops out of the base region. So IE is, this is IE, this is IB, this is IC. IE is IC plus IB. Of course, this is true when we neglect the reverse saturation current that exists across the collector junction, and also, of course, small amount of minority carrier current in the emitter. These two are very small. Intentionally, they are maintained at very small values, so they can be neglected, this and this. Hence, IE is IC plus IB. Another problem, example 7. A transistor has a base current of 15 microamperes and collector current of 3 milliamperes. Find A, gain beta, B, gain alpha, C, emitter current. If the base current is raised by 25 microamperes and collector current by 0.6 milliamperes, find the new value of gain. This is the problem. Solution, it's quite simple. Beta is IC by IB. It is approximately. IC is available, IB is available, so beta turns out to be 200. Alpha is equal to beta by 1 plus beta. Beta is 200. Substituting these values, we can get alpha as 0.995. IE then can be determined by adding collector and base currents. In the present case, it turns out to be 3.015 milliamperes. Now, D. Find the new value of the gain beta when base current is raised by 25 microamperes and collector current by 0.6 milliamperes. Beta is now IC plus delta IC by IB plus delta IB. IC is known, delta IC is given, IB is known, delta IB is also known. Substituting the values, we get some value for beta. Another problem, example 8. Find collector and emitter currents for a transistor with alpha equal to 0.99, ICBO is 50 microamperes, base current is 20 microamperes. Solution. Essentially, we are asked to find collector and emitter current. Alpha is given, base current is here. Alpha is given. From alpha one can determine beta. It turns out to be 99. Beta, by definition, it is IC minus ICBO by IB minus ICBO. This is defining relation. So beta value is known, 99. ICBO is given, IB is given. So substituting those values here, one can find IC as 6.98 milliamperes. Once IC is known, IE can be found by summing base and collector currents. In the present case, it turns out to be 7 milliamperes. Example 9. Another problem. A transistor with a collector junction reverse saturation current of 10 microampere operating in CB is carrying a collector current of 2.98 milliamperes and emitter current of 3 milliamperes. Find the collector current of this transistor when it is operated in CE with a base current of 30 microamperes. Solution. Here, numbers are not manipulated, but the procedure is explained. We are asked to find out collector current. Collector current is given by this one. IC equal to beta plus 1 ICO plus beta IB. First, alpha is determined. Alpha is minus of IC minus ICO by IE minus 0. IC is available, IC naught is available, IE is available. Alpha can be determined. Once alpha is known, substituting in the relation beta equal to alpha by 1 minus alpha, beta can be found. So beta is available, IC naught is available, IB is available. So IC can be found within no time. Another problem, example, the reverse saturation current of a transistor in CB configuration is 0.2 microamperes and it is 18 microamperes when operated in CE configuration. Find alpha and beta of the transistor. We are asked to find alpha and beta. There exists relations for alpha in terms of ICBO and ICEO. Alpha is equal to 1 minus ICBO by ICEO. Beta is ICEO by ICBO minus. These currents are available given. Substituting the given values, one can find alpha and beta without any difficulty. Another problem, example, the reverse saturation current in a transistor is 8 microamperes. If its CB current gain is 0.98, find the collector and emitter currents when the base current is 40 microamperes. Also find emitter injection efficiency, gamma, when the base transport factor is 0.85. Solution process. Beta is alpha by 1 minus alpha. Alpha is given as 0.98, so beta is known. It can be determined. It is 49 in the present case. Then collector current. Beta plus 1, IC naught plus beta IB. Beta is known, ICO is given, IB is. Substituting the given values, collector current can be found as 646 microamperes. Emitter current, as usual, it is a sum of collector current and base. Adding, we will be getting 686 microamperes. Another part of this problem requires us to find emitter injection efficiency. For that, what we have to do is assume an NPN transistor and the part of emitter current that reaches the collector terminal INC1 is alpha into IE. It turns out to be 672.3 milliamperes when B, transport factor, is 0.85. The whole current INE in total emitter current IE is INC1 by B, which is equal to 790.9. Now gamma injection efficiency can be evaluated as INE by IE. It turns out to be 1.153. Same result can be obtained even when PNP transistor is considered. These are the problems which are basically set around large scale current gains of BJT, internal currents, terminal currents, and also their interrelationships. Hope this session is useful to you. We meet again in another session soon with a new topic.